Good morning. As I mentioned in the summation of my bibliography, Keysight Technologies is the oldest measurement company in the world, but also the newest because we were founded in 1939 as part of Hewlett Packard. Back in 1999, we were spun out as Agilent Technologies, and in 2014, we were subdivided again out as Keysight Technologies, whereas Agilent went on doing life sciences products. So, in a nutshell, this is the DNA of the company. We're involved in many, as I said, areas of technology, from smartphones, tablets. Internet of Things is now becoming a massive interest to most of our customers in the communication space. We're involved in cloud and network provision equipment as well. We're also talking to customers about connected vehicles with Wi-Fi standards there. We're also looking into clean energy. In fact, we just bought a company in Germany which I think does battery technology testing. And we're also heavily involved in semiconductor testing as well. And we're also, of course, involved in anything in the aerospace defense markets, from satellites to radars and general electronics productions as well. So we're just waiting for an advance there. The combination of capacities of the company, basically we provide hardware, we provide software layers to enhance that hardware, because many of our customers now are looking for beyond just the basic measurement into applications as well. And one of the, every company says this, but one of our key strengths is our people in our ability to interface with our customers. Just to bring this slightly up to date, in the last 2 years we've acquired two other companies who are probably well known in the industry. One of them was Ixia, which was our latest acquisition, which is focused on network test and security. And we also bought Anite as well down in Fleet, who are more focused on the over-the-air provision. So we're a $2 billion revenue company. We're based in Santa Rosa, California, 12,000 employees worldwide, operating on every continent, and in about over 100 countries. My focus today is to look ahead slightly towards a set-top box of a couple of years' time maybe, or a customer premises equipment of a couple of years' time. And we're seeing, I'm dealing with a couple of customers working on the DOCSIS 3.1 rollout. And the other thing which I'm going to look at today is the 802.11ax, which is the next generation of Wi-Fi, which is still going through ratification procedural bearings. Probably the final standard won't be out for another 2 years. So if the past is anything to go by, we've already seen some vendors who've come out with silicon, early silicon, which is non-standard because the standard isn't set yet. But we're working with those customers to try and get their products to when the box owners, set-top box builders want to be able to make something with them. So I kind of put a pun together about this being cabled and wireless. So we're going to have cable feeding into a distribution unit in the home, and there'll be Wi-Fi or wireless radiating from it. And one of the things, if you look at the DOCSIS 3.1 specification, is, by the way, how many people in here work with DOCSIS? Anybody? A few. How many people work with Wi-Fi standards? A couple. All right. All right, I hope today's not a lost cause then. About 3-4 years ago, Cable Labs, who owned the DOCSIS specification, issued a new version back in the back end of 2013. And this was going to be an evolution standard, 3.1 it was called. Previous standard was called DOCSIS 3.0, I mean, very imaginative. But concealed underneath that very, very small step in the numbering scheme was a massive change in the PHY layer. So DOCSIS 3.0, for instance, used SC-QAM or single QAM modulation, single carrier modulation of QAM standards, going up to 256 QAM. And when customers needed more capacity delivered to their homes or premises, they bonded channels together. So you could take multiples of 6 megahertz channels, and bond them together to get more capacity. When the 3.1 standard was introduced, they decided to go away from SCQAM and go to OFDM. So OFDM has been a fairly persistent technology in most wireless standards since about the year 2000. So we've seen 802.11a came out with using OFDM technology. That was the early Wi-Fi standard at the 5 gigahertz band. Then 802.11g brought that back down to 2.4 gigahertz. Also, things like DAB radio, digital broadcast television, terrestrial, all use OFDM technology. And OFDM was adopted for the PHY layer for the new standard, and you can see here the aims were to provide a headline performance of 10 gigabits downstream. This is operating in the band up to about 1.2 gigahertz, but they also have plans in the future to be able to extend that up to about 1.78 gigahertz. So this was, although named as an evolution standard, it was actually a radical difference in the way that the implementation of the transmission took place. So going to the other side of the customer premises equipment, or any large building, in fact, 802.11ax, you notice with 802.11, they've been through the alphabet once, and now they're going back through the alphabet and adding secondary letters onto it. So we've had AC, which 3 years ago I came here and did a talk about 802.11ac, which was then in fledgling mode. It's now well deployed, and you can go to your local electronics store and buy 802.11ac transceivers. Obviously there's got to be something different about AX for it to be given a new standard name. So one of the key things about this is that we're trying to add into what's called high efficiency modes into 802.11ax. And it's also designed for areas where you've got a large number of subscribers or users of an access point. And at the moment, it's very ad hoc. You send out a transmission and some access point responds, and you try and connect to it and get a service going, whatever. And everybody does that asynchronously, if you like. So it's a collision-based system. So there's no, arbitration, if you'd like, in the access point that allows for the connection of the devices. It's done on kind of on-demand, best effort basis. So when the 802.11ax standard was starting to develop, they decided that they were going to use this both in the 2.4 gigahertz band and the 5 gigahertz band. I'll go to a table in a minute which compares the two. Now, I put up this slide for a fairly important reason. This morning it was mentioned about different Qualm orders and the fact that they have impacts on efficiency. The higher the Qualm order, typically the more symbols you carry per symbol, bits you carry per symbol. So in the case of this 64 Qualm, for instance, constellation, each symbol point that's decoded carries 8 bits. Okay, so if you go up to the next one, which is going to be 2 to the 256 Qualm, sorry, 128 Qualm. That's a weird one because the constellation is not square, it's got bits missing out the corner, and then it goes to 256. So every time you go up another Qualm order, you're adding another bit to the transmission efficiency. So per bit per hertz, you are improving the throughput of the channel. Now, the reason I put this slide up is that in a perfect world, and unfortunately this slide is slightly animated, but in a perfect world, we would have nice clean decision points like that, okay? And if you try to decode a symbol, it's in a fairly stable place each time you see it, okay? However, the world isn't perfect, and you get these kind of distortions. And what we try to show on this diagram is the different types of distortion that occur, and on the left-hand side of this screen, you're seeing the impact or the underlying potential cause of that. So if you see like a distribution which is, a uniform distribution around the point, that typically indicates that you've got a bad signal-to-noise ratio. You've got Gaussian noise being added to the signal. Okay? If you see that the signal or the symbol is pushed in towards the middle, whereas these ones here are fairly central to their decision points, you're probably pushing the amplifier into compression. So you're probably getting some AM to PM conversion going on there as well, which is what happens when, have you got a pointer? Oh, ha, thank you. So when you start to push the amplifier into compression, you also get some phase rotation potentially on the symbol as well. So you're adding to the potential distortions. So in a perfect world, this would be our nice simple decision point. So we get the addition of phase noise typically has a signature which causes a rotation on the constellation points. AM to PM conversion normally pulls the decision point in from the central point towards the center, as you see in these outer states. Typically it happens in the outer states because that's where the amplifier is working the hardest. That's where you see the AM to PM conversion, the compression going on. We also see effects where we get intersymbol interference from poorly constructed filters or poor basebands as well, in which case you see multiple symbols per symbol, but they're clustered together. And then the other one, which is also quite interesting, is when you have a spur tone buried underneath the carrier, which in a spectrum trace it's hard to see, but what happens with the constellation points with the buried spur is that they actually form a circle. So you can actually discern this, and there's other ways of seeing this as well. So I put this up for a reason, because this is common as we go towards the higher order QAMs that we implemented in both 802.11ax and also in DOCSIS 3.1. This problem becomes harder. It has implications for things like the phase noise of local oscillators used in low-cost equipment in the customer premises. So they have to have much purer oscillators, local oscillators in them. Also, it has impacts for the linearity requirements of amplifiers as well. So I just put that one up to bear that in mind as we go through this, because I'll come back to it later as well, if I don't run out of time. So the DOCSIS standard, as I said, is a data standard, data over cable, which is the standard is owned by Cable Labs, which is a collection of cable operating companies. The intention of this, as I said, was to have a more efficient PHY layer based on OFDM instead of QAM. I've mentioned some of this already. And also, it was intended to support the next generation hybrid fiber architectures, whereby the mobile terminating equipment, the head-end equipment, if you like, currently goes over an optical fiber cable to a distribution node, and then from the distribution node, many amplifiers buried in the ground into the cable modems into the home. The intention of the converged networks of the future is going to be IP-based, so you'll find that there'll be IP-based content at the head end distributed to a local neighborhood CMTS over a fiber node to a coax distribution point. So some of that stays common, but the end equipment here and here becomes radically different in terms of the technologies required. So if we look at the downstream PHY layer, it occupies the frequency band from, on the cable, it operates from 108 megahertz to a potential future 1794 megahertz. The bandwidth scale from 24 megahertz to 192 megahertz. Okay, so the widest channel that you can get is 192 megahertz. Currently, remember I said there are 6 megahertz channels which then get bonded. Typically, you might see 24 megahertz of bonded channels allocated. In this new scheme, it will be up to 192 megahertz of downstream bandwidth. So it will use either 4,000 or 8,000 QAM OFDM modulation schemes. The subcarrier modulations will vary in the first implementations from 16 QAM up to 4,000 QAM. So if you remember that constellation diagram I put up where it was only 64 QAM, one of the problems that we get later on when we start to look at 4,000 QAM is that we run out of pixels on our displays, on our monitors. So some interesting challenges there. There's also future extension provision in the standard to go to 16,000 QAM. And some of the folks I speak to are very skeptical about this because they think that the implications for the grade of components is going to be huge. It's a frame signal on the downstream, but it's not bursted, it's a continuous transmission. So if we, the frame consists of 128 symbols, varying from 2.5 to 5 milliseconds in duration. On the upstream side of things, it operates, so this is the modem in the home, the customer modem, back to the CMTS. That operates at the moment from 5 megahertz to 204 megahertz, with bandwidth scaling from 2 megahertz to 96 megahertz. So the upstream generation challenge in terms of bandwidth is a little bit less arduous than the downstream, which is 192 megahertz of bandwidth. Again, this will use either 2K or 4K OFDM modulation. The subcarrier modulations will vary again from QPSK to 4096 QAM. Actually, I say that the subcarrier modulations are going from 16 QAM, but there's actually a BPSK symbol in there as well. In fact, there's two BPSK transmissions. One's the pilot, and one is the PLC preamble, which are also transmitted as BPSK. So when you look at a constellation diagram later on, it's a pretty horrendous thing to look at. One big difference about the upstream signal is it is a bursted signal, so it's not continuous. The modem is told when it can transmit in what's called a mini slot, which we'll talk about in a minute. Multiple users can share a single upstream channel via OFDMA. So here we talked about OFDM, which is orthogonal frequency division multiplexing, and now we've introduced an A at the end, which changes the meaning completely to orthogonal frequency division multiple access. Okay, so this means that there are multiple users sharing the capacity. By the way, that's also true for 802.11ax, as we'll see later on as well. If we look at the downstream signal from the DOCSIS 3.1, a couple of things that we bring out here. The overall subcarrier spacing is this over here, and that's variable depending on the bandwidth being used for each transmission. But some things which are common into each of those channels, there's a thing called a PHY link channel, or PLC. And this is either 8 or 16 dedicated subcarriers in the signal, in the PHY parameters that helps the customer modem to connect to the CMTS equipment. There are some rules that govern its location in the spectrum so that the customer modem knows where to look for it. The cable modem knows where to look for this thing in the spectrum. And it's always transmitted as a 16 QAM signal. Then we got some 0-bit loaded subcarriers, which are active subcarriers that carry no data. They're used to pad out regions of the spectrum where there's no PLC or next. This is another acronym soup, so that we've got things like the physical layer link channel we talked about. There's next code word pointers, the NCP, and there's the code words, and these are always BPSK modulations as well. And as I said, the pilots are always transmitted as BPSK and in specific locations. And there are a combination of fixed and active moving pilots through the signal as well. So the way the system works is that with the moving pilots, they move through the frame so that within 128 symbols, every subcarrier becomes a pilot for a brief period of time. So if you look at this on a spectrogram display, you actually see it walk through the entire channel as these pilots. But there's also some fixed pilots as well. And the code words, each code word, each contains bits for one forward error correction block. Usually one code word is sent per symbol, but they may extend across symbol boundaries as well. And there is a thing called a profile. So each user is served by a profile which defines what modulation scheme you're going to use, what forward error correction, and all those kind of things are sent in. So all of that is communicated downstream from the head-end equipment, from the CMTS to the cable modem, which responds by sending back the transmission it's told it can transmit back. Now, because all of this is structured and sent down to the cable modem, for a test equipment perspective, this is quite useful because it means that if we can decode those blocks of information, we know how to set up the equipment to demodulate the rest of it, because it isn't a trivial thing to demodulate. And as I'll show you some constellations later on, this is quite challenging. If we look at the upstream is sent in groups of subcarriers over symbols, and they're called mini slots. And the idea of this is, so basically it's to give the amount of bandwidth that's required for a particular service rather than giving every single user the same bandwidth and they don't use it. So somebody might be just sending a few messages, you know, instant messages or whatever. Somebody else might be trying to look at a video and keep on responding, or sending a video call or whatever. It's inefficient to give them all the same capacity. So the idea of having this mini slot allocation is to give different amounts of throughput to different users depending on the needs they have at that instant in time. So it's, again, this is what's called OFDMA, so it's orthogonal frequency division multiple access. So the subcarriers are going across here, and this is time going up here, or symbol time going up here, and you can see that any one symbol time, different users are using different groups of subcarriers and symbols. So, from our perspective, one of the problems here is because this is all fairly ad hoc, we're not getting the command messages from the CMTS anymore. Decoding this information from our perspective is much harder. So there are some issues with trying to demodulate that. So this is just a summary of the downstream stuff I've talked about already in one slide. And I think I've covered all of those points. Oh, one thing I didn't cover. I mentioned the pilots are transmitted as BPSK, but one other interesting thing about them is they're transmitted with 6 dB more power than the rest of the modulation scheme. And that is to help the equipment to latch onto it. And if you can't decode the pilot, forget trying to decode the rest of it. It's just not going to work. Right, so if we come to try and demodulate one of these things, and what for our purposes demodulation means to be able to make measurements on it. So one of the key things that people want to be able to measure is the MER of these signals, which is effectively the signal to noise ratio. And to be able to make that measurement, we actually have to demodulate the carrier. So we have to set ourselves to the correct center frequency to catch that transmission. We have to determine the FFT size by looking at the transmission that we first receive. We then have to figure out what the cyclic prefix is being used and find out where the PLC is located inside that group of subcarriers. Okay. Once we do that, we also have to decode the descriptors, which is where the information about the configuration of the channels contained. And the downstream profile descriptor message is also decoded as well. And this is all very useful for anybody who's trying to validate that the messages that they've sent have actually been received correctly, because in the equipment that we will show some screenshots of later, we display those messages as confirmation so that the user can say, I'm testing this thing, I sent this, is that what was received? So from an equipment manufacturer's point of view, we don't do what a cable modem does in the sense that we're not trying to put the data through as quickly as possible. We actually want the ability to take blocks of that data and show metrics of what's going on in terms of distortions or other impairments which are coming through there. So this is typically the process we have to go through. We have to figure out the roll-off factor for the whole thing as well. We have to find the OFDM spectrum location. We have to do the time interleaving, de-interleaving. And we also have to figure out the location of exclusion bands. Right? Now, I mentioned that this 192 megahertz channel can be sent on the downstream. However, if you have to accommodate legacy services which are already existing on the cable, like a DOCSIS 3 carrier or some other carrier, there is provision in the specification to take notches out of the whole 192 meg, so you can turn off some of the subcarriers to let other services persist on those frequencies. So one of the other things that we have to do is to figure out whether that block of spectrum that we're seeing all belongs together, or if there's a notch out of it, is that still a piece of spectrum that needs to be considered as one? So when the exclusion bands are taken out, we still need to say that the rest of what's left over is still part of one downstream transmission. And I said we have to figure out the location of the continuous pilots. I mentioned the continuous pilots, but there's also the moving pilots as well, which we'll worry about later on. So when we're trying to demodulate this thing carrying on, we still have to account for the interleaving in time and frequency. We have to do the next code word pointer demodulation as well. So we're doing the kind of things that a cable modem would do, but we're doing them for different reasons. The cable modem's doing it so it can send the data through to the end user. We're doing it so we can actually make measurements on the transmission that we're receiving. So all of the things that you see on here, we're going to report things like the MER results on the scattered pilots, the continuous pilots, the preamble, the PLC, the next code word pointer, and the data subcarriers as well. So imagine what that looks like, and I'll show you a slide in a minute which shows you a composite view of all of this stuff. So when we went to that single 64 QAM constellation earlier on, imagine an overlay of many constellations, because those things there could be using different modulation schemes on different symbol times. So as you go through the 128 symbols in the frame, different parts of information, pieces of information being transmitted, and we have to have some way of being able to look at all of those in some kind of composite view, or to look at individual parts of that as well. So one other thing that we tend to do as well is the messages which are encoded on the downstream, we show them as fairly simple decoded descriptors. But there are sometimes that the designer of the equipment actually wants to know that the message that they sent was validated. So we actually have a mechanism to go one layer further and do the decode of the messages and export those into an Excel spreadsheet so they can, because we don't try to look at it on the screen because it's a huge amount of data and it just runs for pages and pages and pages, and it comes out as hexadecimal as well. So it's not very user-friendly in the... So when we do our friendly presentation, we decode those hexadecimal messages and give us present our interpretation, but we also allow customers to go down to the hexadecimal string and see the detail if they really need to see it. So we also actually have a requirement in here to report the bit error rate rather than just the MER, which is the signal to noise ratio. Some customers are required to see the bit error rate on the different types of subcarriers that have been downlinked over the channel. So we'll have a look at that. So this is a summary. God, it doesn't show up very well there. Is there any way of magnifying this on this? Is there a mouse? Right, I'll have to talk through it, but it doesn't show. Can anybody actually read what it says there? So in this screen...
How much you pay?
In this screen here, it's basically given us information about what we found in the frame. So that's the MER, the message error ratio. So we're targeting some value better than 50 dB, depending on the modulation being used. This is a composite figure for the entire data, everything else, the pilots, everything is aggregated into this one number here. What we also do further down the screen, down here, is to break down the MER on a per message type basis. So for instance, you can see a pilot MER there, just about, which is always better than the overall, because remember the pilots are transmitted as 6 dB more power. And in fact, we also tell here how much more power than the average the pilots were transmitted with, which is 6.02 dB. And it's transmitted as BPSK modulation, which we can just about make out there. The PLC preamble is also transmitted as a BPSK, but it's actually within the constellation boundary. It's not boosted power levels. So we report the MER for that as well. In the case of the pilots here, it was 60 dB. In this one, it's 52 dB. The PLC data itself, which is a 16 QAM constellation. By the way, down in this little corner of the screen here is the constellation, which is not the best view. Maybe I'll show you a better view of that later on. and then we can see the data just about down here in red. So each one of those that makes up this total number up here is broken out down here so that the user can see at a glance what are the worst contributors to their overall MER performance. Okay? Down here is where we present the decoding of the PLC data that we've seen. By the way, the slides will be available so you'll be able to look at these, but I'm terribly sorry that they're not very visible. I'm not much better here, actually. Is there anything else? Oh, yes. Down here is the spectrum of the carrier. So this one here was a 96 megahertz spectrum that was transmitted. And, oh, yes, there was one active profile. So remember I mentioned about profiles. So here, this is the next code word point. This is the information about the errors on each of the carrier type. So the next code word pointer, this is a 16 QAM modulation that we talked about. This had an MER of 51.85 dB, and the profile A was carrying a 1024 QAM constellation, right? So a bit worse than the 64 QAM that we looked at earlier on. And it was bit interleaved with LDPC low density parity check, and that's the error rate that we were reading from it there as well. But I hope, oh, there's a bit more detail here to so is that any more visible? A little bit.
Just keep it.
So basically this is the decoded downstream message that was, this is what we decoded to set up our demodulator to say, let's look at the rest of it. And inside this information here, you can see that the FFT size was 4096, or the FFT length. There was a cyclic prefix of 1024. That's the roll-off factor. We detected the PLC information correctly. If we don't detect it, we actually put not detected there because it is possible for the user to go into this and define their own. So in other words, if we don't define it, the customer can actually go in and manually define the parameters themselves. It takes a lot longer, but it is doable. We also timestamp every frame of information that we get as well. And we also do a cyclic redundancy check on the timestamp as well. And we do the low density parity check decode, the status of that, it was passed basically. So, where do we get to next? So on the message errors summary screens, this is the results summary screen. Actually, this is a better view of that top corner that I was trying to point out earlier on. This is where we see the overall, then we see the peak value. This is the overall MER, 52 dB. The peak value was here, 38, and it occurred on symbol number 46 in our 128, and it occurred on subcarrier number 2048. So at a glance there, the customer can look at this and say, where are my distortions coming from? Because you can actually go down to subcarrier number 2048 and to that symbol and put a marker on it and say what kind of symbol was that was being transmitted. Down here, this is a better view of the PLC, the decode of the profile information. So here you can see the MER numbers. So this is the signal to noise numbers, and then further down the screen you'll see the bit error rate numbers, and because it was a nice clean transmission, the bit errors were 0. So we do accumulated bits, and we also do the bit error rate. So we show how many bits have been received in error over the observation time and also the error rate. By the way, because of the way that the equipment works, this is a statistical bit error rate measurement, because unlike a piece of real-time equipment, we're not demodulating all of this continuously. We're doing it in observation frames. So we're capturing frames of time blocks of information and demodulating those. And there's a dead time between the processing and the displaying before we see the next one. So this is not what a real-time engine would be doing. But then a real-time engine doesn't let you see the statistics. That's one of the differences. Okay, so a couple of things we did in this engine based on user feedback was we decided we had to have a better way of defining the profiles. So if the customer is transmitting more than one profile, there's up to 13 profiles which are supported in the standard. if the customer wants to define the modulation that's being carried in each profile, it was a pretty difficult thing to do. There was pages of MATLAB information we used to have to download. We added in a much more simple editor so that the customer can say, I'm using a set of subcarriers starting here, ending here, and on that set of subcarriers, I'm going to put one of these modulation schemes. So they can just pick that modulation scheme from a drop-down list, and then when the equipment's then demodulating, it will look for that and say, does that match up with what I've been told? If it then sees that, it then reports that as a confirmed demodulation. Another thing which customers asked for as well was there is a provision in the standard to remove the 5 worst offending subcarriers. So if you have, well, I say remove, from the MER result, there's a provision to remove, or an allowance to remove the 5 worst offenders. So what that basically means is that down here, there's an option to define the subcarriers that you want to remove by their number, or the instrument will look for the 5 worst subcarriers, and when it finds those, it actually puts those into a list and says, I've taken these subcarriers out, and it'll tell you which subcarriers it's removed. The other way around is if the customer chooses this one here, this option here, they can then define the subcarriers that they want in a comma separated string. Right, and this is what I was talking about earlier on about the deep dive for those guys who are working with the DSP engines in the background. This is where you can take the messages at the top level, and then if you see over here, we have a kind of a snapshot view. But if they really want to decode the messages and take everything out down to every single symbol, then we can do this export to an Excel spreadsheet, and then they can take that offline and look at it. And this is just a summary of what we talked about just a moment ago. Okay, so this kind of technical yawn, I think Jasper Carrott once described it as, of colors. Basically, when you see these colors, first you look at them, you think, well, why are there all these odd colors? The reason for the colors is that if I go back to this slide here, we assign a color to each of those types of modulations and messages, okay? So when you see those colors here, and then you see them again in here, basically it means, if you see a red here, that means it's a data symbol. If you see a blue, it means it's a pilot symbol. If you see a yellow buried just about here in there, that's the PLC data. That's the 16 QAM information that's buried in there. And it's basically the reason why we've done this. And when you look at it in the constellation diagram as well, you see it again here. So you see the pilots here. You see the PLC preamble here and here. Then you see the PLC data itself on these 16 QAM, the yellow, and the rest of it is red and data. However, in this particular transmission, there's more than one data type, because what you can actually have in here is 1024 QAM and 4096 QAM carried simultaneously. And this is why I say we then start to run out of pixels, because you don't necessarily see that. I've got kind of used to seeing that there's additional symbols here and here. And if you look kind of close in, you see symbols between symbols. And one of the things we allow customers to do is to be able to just drag, because this is a vector diagram. We decided a bitmap wasn't a good thing to do, because if you do a bitmap, it doesn't rescale. So if you magnify it, you don't see any more information. So these are actually vector graphics. And one of the things that customers said to us when we first showed them this application, they said, why does it take so long when I do the magnification? Aren't you just blowing up the bitmap? We said, no, actually we're rescaling every single vector point again and remapping it. Because it basically means that when you zoom into one of these points, you can actually identify an individual symbol and put a marker on that symbol and get data from that marker. So basically, using a bitmap graphic wasn't a good idea. But if we go to a vector, then there's a lot of re-rendering that's going on in the background. So running this application requires quite a decent PC and also a lot of memory. And in fact, the latest version of this, we've just dropped off the 32-bit support because it's just getting painfully slow. So the latest version just runs in 64-bit. If I go back to a more, composite view of things, these views that we get of the data over here, now this is an interesting one. So this is the MER per a subcarrier, okay? And again, this is where we run into the pixel challenge, because if you look from here, this is we start at subcarrier number 600 and we're going to 3,495, okay? Well, that's how many points? 2,400, 2,000, get this right, 2,800, we're at 2,800 subcarriers. We only have how many pixels across the screen? The total screen? So on this, assuming it's a HD screen, it would be 1920 or something like that, if it's a HD. I don't think it is though. So what happens here is when you see this, it gets a little bit confusing because all the information, there's more than one data point on each pixel. Okay, so again, this is another reason for being able to take that data and zoom it, because if you don't do that, you can't actually see. When you put a marker in there, it's sitting on a point, but you can't actually tell what point it is. So this marker here is actually sitting on a subcarrier, but you can't see what that is. But if you take this little tool here and drag around it, you can expand that and then see the subcarrier individually. And what's actually happened on this here, this is the MER per subcarrier, and this is the RMS MER. So on each one of these subcarriers, there's a number of different symbols stacked up. You see they're going vertically on one of these here. There's actually, on each subcarrier, there's different types of modulation going on. And what the customer wants to know for their results metrics is what's the MER per on each of the subcarriers. So we do an RMS sum of all of these values here and plot them on a graph here per subcarrier. And one of the unfortunate things that we do, which I always turn off actually when I use this, is we draw a bar line from the base to the decision point. If you turn that bar line off, you just see a line of points, and then if the customer wants to know what's the subcarrier, the MER on the individual subcarrier, they just put the marker on that and or tell them. But what's also interesting here is that the markers can be coupled between the different views. So in the constellation here, we put a marker. In this OFDM spectrum, we put a marker. And in the symbol time, this is 128 decoded symbols, we've also put a marker. We've put another marker in the OFDM spectrum, the demodulated spectrum here. And when we assign a marker to a point, we can couple that marker so that, how long have I got? Right.
Yeah.
So how long have I got?
A few more minutes.
A few more minutes, okay. Right, so point about this is that it's possible to view through different displays the same symbol and see where if you see a distortion in one view, it's possible to trace through. Okay, I'm going to skip some slides. One of the things that also becomes an issue with this is when you have two adjacent OFDM channels, there is a roll-off between them, but it's not an infinitely steep roll-off. So there's energy from one still persisting, which can interfere with the measurement of the next one. So one of the things we've had to do recently in the last year or year and a half is to add a DSP filter in here to remove, if we're measuring this channel, we have added a DSP filter to remove the effects of this channel and this channel from the results, because what we used to see was a degradation of the MER at the end carriers only, where they meet up with the next channel. And I mentioned about the effects of exclusion bands. So here's where basically we've had an exclusion band turned on, and this is to allow a legacy signal to come through the middle. And the problem with that is that the energy from that legacy signal can actually cause interference on the channel that we actually want to measure. So we've again put in a new filter in here to remove the effects of legacy signals coming through an exclusion band. Right, looks like I'm going to have to speed up a bit, so let me just... one of the differences, as I said, with the uplink signal is a burst mode signal. So what we have to do here is to actually work in time domain to create a trigger, so we only demodulate when the transmission is on. So here, there's the burst that's being turned on, and we only want to make measurements on that when it's on. And one of the key problems that we have with this is there's a requirement to measure the adjacent channel power. And unless you do a demodulation on the signal to, it's basically quite difficult to, let me take that backwards. When you have a bursted signal, you have a sin x over x response that goes with it, okay? When you try to do an adjacent channel power measurement, some of the energy in that roll-off doesn't go away as quickly as you'd like. So to be able to make a measurement for the adjacent channel, it has to be done in what's called synchronous mode. Synchronous means basically demodulate it and then make the demodulation, the measurement on the demodulated spectrum. So this is what we're talking about here, and this is what we're doing in this view. So you can see an occupancy of part of the time here, for part of the spectrum, for part of the time. We're doing the burst measurements and doing the demodulation on the bursted view. Right, so quickly on to 802.11ax. So there are some similarities between the two technologies. Again, this one here, this is the point about this was to, again, improve throughput. Okay, so we also wanted to be able to improve the spatial reuse, and this also operates in the 2.4 and the 5 gigahertz bands. In 802.11ax, let me just go to the next slide because I think there's a good... this is a comparison of 802.11ac. What's different between 802.11a, AN, AC, and AX? And you can see that the addition of... The things that are in green here are what's new to the 802.11ax standard, basically. So we've added, for instance, longer symbol times. This is to do with combating fading. For if you're using this Wi-Fi out of doors over longer distances, there's been a provision added for having longer symbol times to resist fading better. Okay. Also, one of the things that's changed is the guard interval. So now you notice that the cyclic prefix is, instead of being either 0.8 microseconds or 0.4 microseconds, it's also, we've added in 1.6 and 3.2 microseconds, again, to help with over-the-air fading. Also notice that the subcarrier spacing has dropped from 312 kilohertz to 78.125 kilohertz, a quarter of it. Again, one of the challenges that this means now is that because you've got carriers closer together, phase noise becomes much more of a nuisance. It's much more of a pollution in that kind of system. And also, number of MIMO streams has been increased to 8 in both directions. And also, there's a multi-user MIMO, uplink and downlink, whereas previously it was downlink only on 4 users. And again, we have the OFDM concept on the uplink and the downlink in 802.11ax. And then we have this concept of resource units. So in standard Wi-Fi, a user gets the entire spectrum for the duration of their transmission. In 802.11ax, it's now possible to schedule both the time that they transmit at and also the number of subcarriers that you let them use. So it goes up in blocks of 26. Okay, 26 is the smallest one, and they're typically contiguous blocks of spectrum. Let me just show you in a moment what that looks like. The other thing that's been added into this again is in standard 802.11ac, it's 256 QAM is the maximum currently supported modulation order, the MCS index they call it. However, I do know some people who've been experimenting with 1024 on that on a trial basis. But in 802.11ax, it's written into as part of the requirement that it will support 1024 QAM. So again, problems with closer symbols being close together, difficult to demodulate. So the number of the subcarriers supported, basically we've added on an additional one here. And channel coding is now, we're adding LDPC, low density parity check is now mandatory in the requirement. And what else? Scheduling. So uplink scheduling is now, this is where the access point now starts to act a bit like a base station instead of being a traditional ad hoc access point. It basically tells in that scheduled triggered mode, it tells the stations, as they're called, when they can transmit. By the way, you know when you're in trouble when an acronym includes another acronym underneath it, right? So we have this new concept, or this PPDU, which stands for a physical layer converged procedure. That's the PLCP bit. Then added onto a protocol data unit that becomes a PPDU, right? So this is this is an acronym within an acronym. So this thing supports 4 different transmit modes. The HE here stands for high efficiency, and the the 4 transmit modes are basically single user extended, so that's the distance range. Then there's also multi-user, and there's also a trigger-based multi-user, and also this supports MIMO as well on one of the fields. So the trigger-based one is an interesting one because basically it means that this is where the access point tells each of the stations that's trying to access it when they can transmit. And it has to frame them, so it has to align the timing, align the phases, and align the frequencies as well. Okay, so it's a bit different to the legacy system. As I said, it starts to become more like a cellular base station in the sense of it's now telling the stations when they can transmit. So this is the OFDMA concept, which is where basically, again, on a subcarrier basis, you can either fully utilize, this is OFDM, where user just uses the entire spectrum for the duration of their transmission, for their symbol time. And OFDMA is basically giving variable bandwidths, a bit like we saw again in the DOCSIS 3.1. So there are some similar concepts that come through there. Here we come across something called a resource allocation unit, or an RU. And basically these are blocks of subcarriers of 26 subcarriers, typically. So all this table is doing is basically telling you for each of the different bandwidths supported in 802.11ac, how many 26 subcarrier resource units can you use, how many 52 subcarrier, how many 106, etc., etc. And then there's a diagram here which kind of shows graphically how those could be utilized in different combinations. So the multi-user resource allocation unit on the downlink, basically, here's a SIG-B field. Oh, I should have mentioned, by the way, these fields out here, if you're supporting legacy devices, they transmit those fields only. So the station knows that it's dealing with a backwards previous revision of the standard. The high efficiency fields get transmitted by the newer devices to identify that they support the new capabilities. If the access point doesn't see that transmission, it says, I can't support those, or those devices can't support those modes. So there's some new fields that have been added into here. Let me just bring up all of those. And when the access point decodes one of the fields from the, it basically tells the mobile, the stations, as they're now called, what they can transmit and when, depending on what kind of services they're trying to access. And there's a bit that gets set in the B field, in the SIG-B field, in the compression field. If that bit gets set to a 1, it tells this whole system that it's going to use MIMO for one user instead of the OFDMA access. So those two modes are kind of exclusive to each other. So depending on, I'll let you read these at your leisure. The triggered frame, as I said, is the challenging one because this is where you have to have that alignment of time, phase, and frequency for all of the subcarriers. Bearing in mind that you might have different propagation delays over the air, depending on how far each user is from the access point. That basically means that things like timing delays between those has to be estimated now, and some kind of timing advance may have to be implemented to be able to frame the data at the access point when it's received. Okay, this is the different modulation schemes. Do you remember that diagram? Okay. That diagram there basically is telling us that, one second, for each of those different modulation schemes, this is the signal-to-noise, theoretical signal-to-noise ratio required to support that successful decoding of those signals. So I think I'm going to have to wrap up there, but at the end of the, there are some reference materials in here, which I've pointed out, which you can access right at the end. So there's some reference material which you can access to if you want to find out more about how this thing works. Okay, and I've put some live links in there as well, so if you click those red links, it should take you to the resource. Okay, I'm out of time, so sorry about that.